All right, Advent of Code 2020 day 10 starting now. Okay, aircraft charging outfit has a joltage rating, heavy adapter, yeah, be higher than the highest rater. I see. 0 joules. Okay. So we just need to like sort these, right? Oh my god. Want and 1 times M3. Damn it. Oh. Reading is hard. We should use the sample data. So this one got, oh, why did that happen? Let's see. Still only 25 with the wrong answer. Okay. How many different ways they can be arranged? You need to use them all? I guess not. $19,208. That's too slow because I need to memorize it. That's a number. Okay. So painful long answer in part 1, but overall actually pretty good. So what's going on here? So we have this big list of numbers, and the rules are that you can step from one number to another as long as the difference is at most 3. And we want to get from 0 to the max plus 3. right? That's what this is saying. What does it say, 0? Yeah, 0. And you can go up 1, 2, or 3, and we want to get to max plus 3, which it says somewhere. Sure. Okay. And so in part 1, the question is just if you use all of them, fine. That's how they make it unique. What is the number of differences of 1 multiplied by the number of differences of 3? So of course, to use them all, they had to be in sorted order, right? Because they can only go up, right? If you go up 1, 2, or 3. So we just sort them, and we take the differences, and we count how many are 1 and how many are 3, and you just multiply them together. So part 1, straightforward. You do have to remember that the difference between 0 and 1, like the 0 counts, even though it's not on your list, right? That's the charging outlet. And the max plus 3 counts, even though it's not on the list, which is the goal. So I just explicitly added both of those to the list. So count the number of 1s, count the number of 3s, and multiply them together. That's the answer. Right? And my bug was that I forgot to add those to the list. For part 2, it's more interesting. Right? There's an algorithmic idea here that probably some people haven't seen before. So the question is just how many ways are there to climb up through the whole list? And basically, you're allowed to skip things, right? So how many ways are there, including skipping? And we can solve this with DP, which is an abbreviation for dynamic programming. So let me explain this in a little bit more detail. So first, this is not the only way to think about DP, but it's a good way to think about it. So I'll just explain this way of thinking about it, which is that first you write down a recursive brute force solution. So in this case, I have this function, which I've unhelpfully just called DP, which means the number of ways to complete the adapter chain, given that you are currently at adapter x's I. Okay? This is like an extremely concrete definition, right? Like clearly this function exists, right? If you're at 15, there's some number of ways to get to 22 from 15. That's what DPI is counting. So if you are already at the end, then you're done, right? There's only one way to get to the end, which is you're there. So return 1. Ignore this for now. And just, so how would you do this with the recursive brute force solution? Well, you just try all the possible next adapters, right? So you can step to anything bigger in the list as long as the difference is less than 3. And if that is true, then one way to get from, this is worth writing down. The number of paths from I that start by stepping to j is just dp of j. So dpi equals sum over, let's say, valid j of dp of j. Right? This is a recursive formula for dpi, and it should be clear why it's true, right? It's this reason. From I, you have to take a step to somewhere, and once you're at that new place, the number of ways that you can get to the end is counted by dpj, and so the number of ways that you can get to the end from I is just pick the next step you're going to take, and then sum over the ways to from that place. This loop, by the way, is a bit silly because obviously, I should only check j up to I plus 3 or something, right? Or at least I can stop checking j once it's more than 3 away, since it's sorted, right? It's increasing. But whatever. It really doesn't matter. This input list is only 100 numbers long, so this makes our solution n squared instead of n, but 100 squared is nothing for a computer. Okay, so now the answer is dp0, but there's a big problem, which is that this recursive brute force solution is exponential time. And why is that? So imagine you just had all of the numbers, you know, in your input list, right? Then you can take steps of size 1, 2, or 3. What's a good way to see why that is? Like, how many ways are there to get... Okay, I'll put it this way. From 1 to 4, there's at least 2 ways. Well, let's say there's at least 3 ways to do that, in fact, which is 1, 1, 1, 1, 2, and 3, right? A single step of size 3, a step of size 1, and then 2, and then or 3 steps of size 1. All paths from 1 to 4. And then from 4 to 7, there's also 3 ways, right? So from 1 to 100, there's, you know, 3 ways to get to 4, and then from 4, there's 3 ways to get to 7, so there's actually 9 ways to get to 7, and then from 7, there's 3 ways to get to 10, so there's like at least 27 ways of getting from 1 to 10. It just increases exponentially, right? The number of paths. Another way to see this, or interesting fact, is that if you just could take steps of size 1 and 2 when you had all the numbers, then there's Fibonacci number of ways to get from 1 to n, which is also exponential. Anyway, whatever. It's definitely exponential, and I guess another way to see it is just try running it, and like it's too slow, right? It's just not finishing. Another way to see it, I guess, is that this is the actual answer. This is the number of paths, and this is a huge number. If we count the paths one by one, we're never going to finish, because this number is absolutely enormous. It's like, you know, this is hundreds, this is hundreds of thousands, this is hundreds of millions, this is hundreds of billions. So this is 18 trillion paths. Computers cannot count to 18 trillion in any reasonable amount of time. Maybe if you gave them a few hours, they could do it. So we need to do something smarter than this brute force solution. And this is where the other half of DP comes in, which is memoization. And so the observation is that once you're at, say, 7, you don't really care how you got there. So, right, the problem, the exponential growth that we previously identified was that we were tracing out every single path, effectively. That's what this does, if you think about it. But, you know, there were 3 paths to 4. Once you're at 4, you don't need to reevaluate DP4 3 different times. You could just calculate it once, remember the answer, and return it all the time. And that's exactly what we're doing. So we're just saying, if you've already figured out how many ways there are from 6 to the end, then write that down. That's here. And if you've already written it down, then just you return it instead of recomputing it. And that has a dramatic effect on the running time. It brings it down from exponential to linear, or quadratic, actually. I already explained that this loop is sort of dumb. But not exponential is the point. And the reason is that this function only runs like 100 times, or like len of x's times, right? Because there's only 100 different values of I. And once you run it once for each value of I, it's this trivial thing where you just look it up in a table, or in a dict in this case. So this part only runs 100 times, and this is only 100. So the whole thing is only 100 squared, right? And this part, well, we're already counting that in the 100 times that DP runs. So that's the way to think about the running time of DP, is just how many times do you call the function, how many different states there are, or inputs there are, and how much work do you do, non-recursive work do you do in the function, which is just here. So that gives the n-squared solution to part 2, which runs like super fast, right? A fraction of a second to count to 18 trillion. That's day 10. Cool DP problem. And pretty good placement by me. So overall pretty happy. Would be happier if I hadn't messed up part 1, but yeah, pretty good. So that's it.